Okay. So let's come in and take a look at some of the multiple group models on various software platforms I talked about. Before I get started with that, I wanted to highlight some of my comments about growth curve modeling and linear growth curves. Let's just consider a here we go, interface. I want to make this landscape just because that looks better. If you're playing with Onyx, I'm sorry, if you're playing with Amos, it has a small there tool over here in the upper left-hand corner where there's a plugin called Growth Curve Model. And that works really nicely. It'll draw your growth curve model for you. You can come in and say, how many time points do you want? And we might say, for example, oh, let's say we have five measurement occasions in our study. And automatically, Amos will draw you this growth curve model for you. And the thing I'd wanted to draw your attention to is the slope factor. So in some respects, this does some nice things for you. It sets all of your intercepts to 0. And then it says, I'm going to have an intercept mean, an intercept variance, and slope mean and slope variance. But my point here about not letting the plugin do your work for you is if we come over here and take a look at the numeric values they use for slope, these are the values that the program has selected. And what it's doing is the first measurement occasion is 0 and the last measurement occasion is 1. And then it does equally spaced steps from there to there. And that in your particular study may not be what you want to do, particularly if there's unequal measurement occasions between the unequal amounts of time between the measurement occasions. If, for example, this is a 1-year follow-up, but this is a 2-year follow-up, and that's a 3-year follow-up, you don't want to have numbers there that correspond to equally spaced steps. So you'll have to figure out what fraction of the total time period measurement occasion 2 is and fix it to that value if you want. Alternatively, if you want to adopt a measurement scale, like you want to have these numbers be fractions of years, sometimes that's a little bit easier to write up and describe to people. But that's all I intended in saying that you can't necessarily ride the defaults of the software. In those cases where you can, this makes things a little faster for you. The other thing I would like to do is to walk through a multi-group model. And here is a multi-group model that we have in Amos. The reason I'm starting off with Amos is because students, when they see it, often say, oh, this is the way I want to do my multi-group model, because it does an awful lot of things automatically for you. What I want you to take a look at is inside of the Amos diagram, we've got, I think I'll make this larger. We've got, instead of one group, we've got 2 groups here. So if, for example, I come in and take a look at my data files, there's a college group and a no college group. And these are summary statistics. I can open them up in Excel and show them to you, or you can open them up. I've sent them all to you. And you can either put them in separate files or inside of your data set if you have a variable that says males and females. You could access one file and say there's a grouping variable and say it's sex, and then say group value, maybe 1 for females, 2 for males, or something like that. And Amos will go in the background and figure out who your males and who your females are, your younger, your old people are. These are summary data, and it's taken from John Lowland's structural equation modeling book. So in order to do multiple group models very quickly and cleanly, you'll notice that this diagram doesn't have any variables present. So I can click on the college group or the non-college group, and there are no parameters named in here except for the paths from the errors to the manifest variables. And that's generally a good way to do these things because the program is going to go out and assign all of your parameters for you. And the way it does that is to come into the model, and we'll click the Analyze button and select Multiple Group Analysis. And it gives you a warning, and it says, this is going to write over your diagram that you have. Are you sure you want to have that? And you say, okay. At which point it then says, how do you want to set up your multiple group comparisons? And in this model, I don't have any means or intercepts in the model. So you'll notice that the measurement intercepts in the diagram are grayed out. I can't select those, but it does let me say, are my residuals going to be the same across the college and non-college populations? Are the covariances in the diagram going to be the same or not? And are the measurement weights, that is the factor loadings and any other arrows I have going on, going to be the same in the model? And in your adventures in your particular diagram, you might have other models that you will want to select. It doesn't make a whole bunch of sense, but you can just click arrows here and select which things you would like to hold across the two groups. And this extends to 3 and 4 and 5 groups if you'd like. And you say, okay, at which point it has now gone into both of my diagrams and labeled everywhere where it saw a free parameter value, it's given it a name. I think, some of the mnemonics for the parameter names are a little bit unfortunate. I don't know why covariances are CCCs, and why variances on latent variables are VVV, but such as it is, we got it to do a lot of work for us. And you'll notice that the parameters are different across the college and the non-college group. So I'm looking at the college group, that's group 1. If I click on non-college, I'm going to have group 2. I used to have an instructor who had the annoying habit of saying, and if you hit the run button on it, this isn't going to work. Well, and not to echo George Terwilliger, but if you hit the run button on this, it's not going to work. And the reason that it's not going to work is this model is not identified, because if we just consider the college folks for the moment, there's a freely estimated factor variance here and 3 loadings. So we're going to have to tell the computer program in one of these groups, I want to make an identification constraint. And the reason I do this is, the reason I set this up this way, it's different than you'll see other people setting it up on the internet, is I can then come back and say, well, what if I identified my model by fixing a loading to 1? And would that change any of the outcomes? Over here in the middle, you'll notice that we have several models. The unconstrained model is entirely blank. It doesn't have any constraints in the model. The measurement weights button, though, model, has the factor loadings being the same. So A11 is in group 1 is equal to A1 in group 2, and the same song for all the other factors. The structural covariances has all of my loadings plus all of the covariances in the model and all of the factor variances. And the measurement residuals has all of that plus the error variances across these things down here. Okay. So, it did all, and all of the error variances associated with the manifest variables. So it's done a whole bunch of writing. This is writing that you could just as easily do yourself, but this saves you some time, which is why people kind of like Amos. So let's get this program into a form that it can run. Well, in order for us to do that in the unconstrained model, I'm going to have to say across both of these groups that the factor variances are going to be equal to 1 in group 1 and group 2, because in this model, move it over here, this factor variance is freely estimated, and in the non-college group, that factor variance is freely estimated. So inside of this model, I'm going to come in and say VVV1 underscore 1 is equal to VVV1 underscore 2 is equal to 1. And I need to say the same thing for factor 2 and factor 3. So we'll come in and do that. Wait a minute, I'm changing the wrong one. Okay. At which point, if I hit the run button, my unconstrained model should run. Let's try that out. Oh, I've got to go in and read the tab delimited versions of the data. Sorry. So this is the college group. Thank you. And down here, this is the no college group. Okay, so this is what the data look like. So now I should be able to hit the run button. And you'll see that I have a little OK here, and it gave me some numbers. And across the college and the no college group, everything about this diagram is going to be different. So, I've got 85 up here and 79 down there. And the other group, I've got 161 and 90, so forth. So in order to have the rest of my models run, I'm going to do the same thing for the measurement weights. Now, this is now going to say the measurement loadings and the factor variances are the same. But one thing I can get away with now is the model becomes identified if I set the factor variance to 1 for one of the groups and freely estimated in the other. So the change that I make here is that I'm going to remove, I'll move this into the middle for those of you watching at home, I'm going to remove the requirement that the factor variance for group 2 needs to be 1. Okay. So we can hit the run button now, and we can take a look at that, and we see that it's okay. And across the college and no college groups, I have the same factor loadings. And the reason that the requirement that measurement intercepts be the same across the groups is a useful one, is you're able to summarize group differences by reference to the factor model. So in this model, we don't have the mean in the model yet, but we can say that I've got the same loadings here across group 1 and group 2, but the non-college group appears to have a lot less variation in factor 1 than the other group. Excuse me, I want to move the parameters around here. Okay. And in that way, you can summarize your multiple groups by saying, these two groups have the same factor loadings, but it's the case that the other group has substantially less or more variation than the other group. The reason that I spend a little bit of time talking about this is if you're looking on the internet and you have people doing multiple group invariance studies, very frequently they don't notice that they get to free up those factor variances. And as a result, they're fitting a model that's too restrictive, mainly because they're kind of copying and pasting what's going on. Any questions on that? So we'll come back downstairs here, copy this, and come down to structural models, where we can now again paste our requirements on that. And now inside of this, I've got the variances, and downstairs you'll see, oh, the variances are constrained to be the same. So this code I have up here, that it's 1, is going to carry it down to here and say in group 2, the variances are the same, and also the covariances, that is because the variances are constrained to 1, they're really correlations between the factors are the same across the 2 groups. And if I hit the run button on that, you'll see that that should now run. And copying and pasting again down to the measurement residuals. Here's that requirement, and I can hit the run button again, and that will all run. But wait, there's more. Now we can come into the spreadsheet, and it will show us all of the models. In terms of the graphical interface, you can either be looking at the college or the no college groups. And downstairs in the lower left-hand corner, we have the invariance hypotheses that we were looking at. So for example, for the unconstrained model, I can come in and look at my parameter estimates if I wanted to. Downstairs here in the model fit situation, I've got the fit statistics that correspond to my multiple groups. So in here, we're looking, for example, at the chi-square. This is a study that was relatively small. All of the chi-squares for the models, except for the measurement residual model, are non-significant. So you might get away, concluding in your paper, hey, the variances of the factors, the correlations of the factors, and the factor loadings all appear to be kind of the same. And downstairs, if I look at the TLIs, the TLI fits for all of those models are great. And the CFIs are also great. So again, you might say the model I'm going to check off is the structural covariances here. And downstairs, I have the RMSEA. And as we talked about before, these are indicative of nice fit. And here's our confidence interval and the probability that the centrality, the RMSEA is less than 0.5 is also fairly good. And then downstairs, this is the one that takes a little bit of talking for a moment, is we have our chi-square difference tests and the other incremental fits for the comparisons. So in terms of the chi-squares, we have a slightly different pattern of results than the standalone fits. So let's walk through this at the beginning. The unconstrained model, if that is our model, we're now going to calculate a chi-square difference between the unconstrained model where everything is different with the structural covariances model. And that p-value is significant. So that indicates that you have lost, you've gained some explanatory power by letting everything be free. And, that's an O3 effect. It's a very small effect. And the measurement residuals, well, clearly that's not at all good. So that chi-square's difference test is very large. And then if we assume the measurement weights, in this case, the factor loadings are the same, these are the chi-square differences for the structural covariances and measurement residuals. And again, based on a chi-square difference test, we would say, hey, these things are actually different. And way down here, if the structural covariances, that is the factor loadings and the variances and covariances of the factors, are constrained to be equal. Adding the measurement residuals also gives me a significant chi-square difference. All right. So that's a lot of talking on my part, but that walks you through how to do a multiple group analysis. You got some questions for me? It's all perfectly clear. Well, if that's okay, let's come back and take a look at the Mplus system. Can you hear me? It's been very quiet, so make a noise, somebody, and I'll know I'm still sending things out.
Yes, we can hear you.
Okay, good. It's a little like a seance. Are you out there, class? Give me a sign. But
yes, we are following you.
Okay. Well, so here's an example of the same setup, again, using summary statistics for the same data set, but using the Judd and Milburn data set. Now, the difference that you need to think about for this is that by default, Mplus conducts multiple group invariance with the mean in the model. So let's walk through a little bit of the code here as to how these things are a little bit different. I made a summary data set, Judd and Milburn.dat, which consists of means, standard deviations, and correlations. What makes this a multiple group model is my statement of the number of groups equals 2. If I'm inputting summary statistics, like somebody's correlation, I'm also going to have to say the number of observations. If I have raw data, as most of you might, you would be saying grouping is, and then you'd say what variable is the grouping variable, like sex. And that would be all you'd need to do. You wouldn't have to say how many observations there and so forth. You would just be reading in the raw data. Recall that Mplus does not take variable names in the file. Instead, you have to declare what they are. I guess I should have said, this is, given the political nature of our days, this is a study of liberalism from 1972, 1974, and 1976. And we're going to do a maximum likelihood estimation. For doing our model, we have this little statement. So as we talked about in Amos, this will model configural invariance. That is, the factor loadings are the same across the true groups, but the numbers involved in the structural equation model are different. Metric, in which case we're looking at the factor loadings only being the same, and scalar. And we'll walk through exactly what that is. So it's going to, just like Amos, it's going to now in the background go through and program these three models for us. And I wrote a model statement down here, and I had a reason for doing so, that in Mplus, one of the nice things, and sometimes one of the frustrating things about it, is that Mplus will fill in the rest of the model with what you think should be there. So in this model, I said, here's a factor, it has 3 indicators. Here's a factor, it has 3 indicators. Here's a factor, it has 3 indicators. Oh, and by the way, the factors have some correlations. And it's going to go in and fit the model for us. So let's hit the run button and take a look at our output. It gives me the chi-square statistics for my 3 models, the configural, metric, and scalar. And it gives me chi-square difference tests. And the way to parse this is to come back and look at the individual models and see what's the same and what's different. So it gives me the fits for all my little metric models. Here's the configural model. Well, this configural model by default is going to fix the first loading to be 1 and freely estimate the factor variances. And that's okay. It's a legitimate way to proceed. You may get slightly different results in more complicated models by making slightly different choices about identification. Notice what happens to the mean here. All of my factor means are 0, and all of my intercepts are freely estimated. So as we've talked about before, this is equivalent to just doing a covariance model. These intercepts are different in group 1 than in group 2. The factor mean in group 2 is also equal to 0. So, the configural model is an easy way of talking about factor structure across 2 groups. The question in your head conceptually is, even though the pattern of loadings is the same across the 2 groups, is the status, is the interpretation, is this latent variable really the same latent variable from one group to another? Because the factor loadings are so different. So let's come down to the next model and look at what stays the same and what differs here. Well, in the metric model, I've got 1, 6, 8, 5, and 7, 4, 1 in the first group. And down here, I've got 1, 6, 8, 5, 7, 4, 1 in the second group. That is, the factor loadings are the same. Upstairs on the factor covariances, 8, 3, 7, 9, 4, 1. In the other group, 223, 217. So the factor variances and covariances are quite different. The means of factor 1 and group 2, factor 1 and factor 2, are still freely estimated. That it's 0 here, and the intercepts that I have for the manifest variables are different numbers down here. And here's my intercepts here and my means here. The residual variances are also different things, 692, and then down here, 1524. The scalar model is our last one. Well, all of my loadings are going to be the same across the 2 groups. Notice that the mean in group 1 is 0, and my intercepts are freely estimated. And in group 2, the means are freely estimated. So that's a little bit like what I was showing you in Amos, that as we set it up, we can now say the means of my variables of the non-college group are significantly lower than the college group. Your conceptual interpretation would be students or young people who did not go to college are significantly less liberal than young people who did go to college. Similarly, the variances among the non-college group are also rather large. That is, their scores are much more, in addition to being lower, they're also much more variable. My residual scores are freely estimated, 681 and 1492. So the error variances are different. At the end of the day, for when you're thinking about a structural equation model with a mean in it, maybe, this last model of scalar invariance is kind of what you'd like to land on, because it's saying the factor variables are the same things, but the latent variables show some differences from group 1 to group 2, and the error variances are kind of different across the 2 groups, but we really don't care that much about the error variances themselves. Now, let's get out of the output here and come back to our model. Notice as I've drawn this that I didn't draw any error covariances. So if we were to do that, B72 with B74, and B72 with B76, and B74 with B76. This would then give me my error variances. Right. See if I'm counting these right. So this would be C, 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 and J, J, J. And over here, excuse me, C, 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 and J, J, J. And this will then give me the same results as I saw inside of Amos, except that the factor loading was set to 1. Now, if you want to go on in your invariance models inside of Mplus, as far as I can tell, I think they might have the word strict, in which everything would be constrained, but you might be in the position of having to actually write the individual code for doing those models, the individual invariance, multiple group invariance models. I just thought I would give this to you as an introduction to the fact that Mplus now does these things just as easily as Amos does. The other platform that people play with is R. So let's take a look at that. I went out and stole the summary statistics from John Lowland's and Alex's website, and then I went back to the original article and stuck the means in. And it's worthwhile to talk a little bit about the R code for putting summary data into a structural equation model. So this sets my working directory to be where I'm doing the work. Comments in R are started with a £, and I can then read in my correlation matrix with 9 columns of data, and that will, go out and suck through all of the correlations for me. And I can then say that the row names and the column names of this correlation matrix are as follows. And here's a vector of standard deviations. And then I went out and I pulled this vector of means. And this and then I do the same thing for the college group. This gives me my college folks and the same names and the standard deviations for the college group and the standard deviations, the means for the college group. So let me just kind of run all of that for the moment. At which point I say, oh, I might want to do lavaan. At which point I use a function that changes a correlation matrix into a covariance matrix. It takes as input the correlation matrix and the standard deviations. And say jm.call.cob. That gives me this matrix, this covariance matrix. And if I then want to combine the summary information, I take my covariances and I just put those into a list. And I have to say what the sample sizes are for the list. And then I have to say what the means are for the list. So here's our model, which will fit the structural equation model. And to start things off at the beginning, I thought, let's just run it based on the no college group to run an example. The name of the model is 4.3 because that's the name of the example in the book. And this is equivalent to my by statement inside of Mplus. My latent variable is a function of these 3 manifest variables. For those of you who don't play with R is picky about case. So if you start using an uppercase for something, you have to keep using an uppercase for something. It's a strongly typed language, as they say. And by default, like Mplus, lavaan is going to assume, unless you tell it otherwise, that the first loading has identifies the factor by fixing it to 1. Inside of this, they decided to do some regression, so they're predicting 1974 from 1972 and 1976 from 1974. Downstairs, I have my residual covariances between 1972 and 74 and 76, and 1974 and 1976, and I do that for my 3 manifest variables. I sure am talking a lot today. Maybe I've had too much coffee, but let's just run that model. And we can then fit this model. So this is the name of the model. And this is the sample covariance matrix you should be looking at. And here's the sample means. And this is the sample size number of observations. And you can then run that. And then we can take a look at our summary statistics for the no college group, at which point it gives us the chi-square, the degrees of freedom, the standard errors, and so forth. And here's our parameter estimates. We can ask for standardized ones if you'd like as well, but that fits all of those for us. And if you're going to fit invariance models, we'll have to run them in sequence. So in order to run our unconstrained model, we're going to say, I'm going to put in all of the covariances, all of the means, and all of the sample observations that I put in above. And that fits my configural model. I can take a look at that. And now as in somewhat distinction to before, I'll get all of the loadings out that I had before, and the loadings in group 1 are going to be different than in group 2. So for example, I have 585 in group 1, and downstairs here in group 2, I've got 1.12 as we had before. The variances are going to be different across the groups because I identified the model by fixing the first loading to be 1. So down here, where am I at? Here's my variances. 2.586 in group 1, and down here, 0.620 for group 2. And if we now want to fit our invariance models, we're going to use the group equal command. So subject to the way I identified the model, this now fits a model in which across groups, the loadings are the same, any regressions are the same. In this case, we had arrows joining 72 to 74. Latent variable variances and the residual covariances are the same, and the residuals. So this is a fully invariant model saying group 1 is just like group 2. And I could look at a summary of that as well. Combine fit 2. At which point, here's my numbers. So note the parameter names that will indicate the equality constraints that I placed in the model. So that P2 is the same as this other P2 downstairs in the second group. And, as I mentioned before, the estimates are all, constrained to be the same across the true groups as well. And that basically is how you get started with the code. If you go out to the website and take a look at, the book, this is the code they give you. If you want to put the mean in the model, we're also going to say that the intercepts and the means that are present in the data are the same. So let's come downstairs and run that for the moment and take a look at what we get out. Oh, wait a minute. Ran the wrong one. There we go. At which point, here's group one. Here's our regressions, just the same as we had before. Notice our intercepts now, our manifest variable intercepts are the same. Parameter 33, 34, 35, and down here 33, 34, 35, and so forth. So my intercepts have been constrained to be the same. Let's see, where are my means? And here's my means downstairs. In the second group, I've got zeros, and in the first group, I've also got zeros. So that's saying everything is exactly the same across the two groups, means, intercepts, everything. I could come back upstairs here and fit another model that says that the intercepts are the same, but that the means are actually different to mirror what we did before in Mplus. So now here in group one, we've got our intercepts and our means. And if God is in heaven downstairs, I've got the means of the latent variables, 72, 73, 74, freely estimated in the second group, which is just like what I had before. The reason this is different than the other one is I explained this model has autoregressive paths from 1972 to 74 to 76. There have to be some show me this again parts or tell me what I'm doing parts. It gives you your code, though. Well, I sort of chatted nonstop. So let's come back in here and take a look at this model inside of Amos. In the original book, in the original article, sorry, the way they fit this model, let's come back in and take a look at the clean version again. They had said the model looks like this. And that has perhaps some explanatory power. You could say group one, your liberalism in 1972 influenced 1974, which in turn influenced 1976. But that's only one way of thinking about the data. So as an illustration of the state trait model, another way to think about the data is to consider it as follows. Like this. So it might be the case that we don't have autoregressive effects over time, but that there is a stable trait, that there are some people who are just more liberal than others. And if we fit this model, well, we're going to have to think about how we wish to identify this model. Given that I've got like 4 more minutes, let's just walk through some of those steps. First of all, these 3 factors are now endogenous. So I can't come in and say I'm going to fix one of these disturbances to 1 to identify the model. If I'm playing with lavaan or Mplus or Amos, I'm going to have to if I'm playing with lavaan or Amos, I'm going to have to fix one of these loadings to 1 to make this factor identified. Upstairs, I need to play the same identification game as I would play as if these were manifest variables. That is, I can fix this trait variance to 1 and freely estimate these 3 loadings, and then freely estimate these error terms. This gives me 3 this part of the diagram then becomes a statement about the variances and covariances among 3 latent variables. 4 times 3 is 12, divided by 2 is 6. So the most parameters I can have upstairs is 6. 1, in terms of an error variance, an error variance, an error variance, a loading, a loading, a loading. Well, that's 6. I can't have any more free parameters than that. But, in terms of the model, multi-group model, this is going to be slightly different than the correlated factor model that we had. We can now say there are differences, we can start to test, is there just more or less trait liberalism in the college and non-college groups? And these error variances down here talk about liberalism that was unique to that particular year. So 1976, for example, was the year I think that Jimmy Carter got elected. It was a presidential year. There might be some variation at that particular measurement occasion because it was a presidential year that is documented by this disturbance term for this factor that does not apply to all measurement occasions. And, we can again set this up as a multi-group model. We don't have time to run through today, but I can, if you want, start it off the next time. I realize I'm talking too fast, but, I tend to make too much to talk about in class. The other thing that you might want to notice about this model is that we have the same variables measured over the course of time here. And as we have set this model up, and as a matter of fact, as everybody analyzing this data has considered, they've never really thought about longitudinal invariance. Maybe it's the case that this C72 loading is the same as C74. So next time we'll talk about invariance for longitudinal data and how you would set that up, and then progress toward building a single model that talks about invariance across time and across groups. The other thing that we haven't done in this model is to say, well, this model, as it's drawn here, does not really talk a lot about growth of liberalism or decline over the course of time. Well, we're going to put the mean in the model then. Where you put the mean in the model then becomes your choice as to what you want to document. If I estimate a trait mean and have that do the double duty of not only explaining patterns of covariation between these 3 years, but also mean level, this trait becomes a factor mean model for growth over the course of time, growth or decline. And our assumptions about measurement here are something we're going to have to think about as we build that general model. Well, so